Good morning to all guests and students. It is with great pleasure that Palamuru University welcomes the one-day national webinar on lecture series on spectral techniques. It is organized by Department of Integrated Chemistry. Welcome to all Professor Pindi Pawan Kumar sir, Register Palamuru University, Dr. D. Madhusudan Reddy sir, OSTU Vice Chancellor, Dr. M. Nurjahan Madam, Principal University PG College. Our university is honored and delighted to support this meeting, and I should like to personally each and every one of you being here. Moreover, I thank Pawan sir, Madhu sir, Nur madam, and convener K. Ramon sir, and dear colleagues. The schedule of this conference is rich contents and subjects, and I think it will be for its attendance a very impactful experience. This because I would like to thank all speakers. Professor S. Jagannatha Swami sir, former registrar and HOD Chemistry of Department, Kakatiya University, topic UV spectroscopy, and Professor M. Vittal sir, former Professor of Chemistry and Basic Science Research Fellow, Usman University, and third speaker Raghu Chitta sir, Assistant Professor, Department of Chemistry, National Institute of Technology, Warangal, and Professor Girija Mangatar Madam, former registrar and BOS, Chairman and Department of Chemistry, Palamuru University, Mahbub Nagar. And I thank each and one who is aware of this meeting, Reliance Society, evolving, learning, innovating, and investing knowledge. These topics are very useful to students and faculty fraternity and utilize this wonderful opportunity. Next, I invite K. Ramohan, Department of Integrated Chemistry, Head of the Integrated Chemistry. He is doing PhD in Usman University. He has 10 years experience, teaching experience. He will preside over the program. Thank you.
Today, nice day. A webinar is an online event. Speakers deliver a presentation to the view a platform, valuable information are students in the world. Webinar provide a wide variety students, their skills, their understanding of their subjects, and students are participants to attain knowledge and get effective learning. Sorry for the inconvenience, sir, and the participants. So today lecture series on spectral techniques gives vast informative knowledge in the chemistry as well as towards industry to the students. Like UV spectroscopy can be used for the quantitative determination of compounds such as highly conjugated organic compounds, and infrared spectroscopy is used to determine functional groups in molecules, and two-dimensional nuclear magnetic resonance spectroscopy is used to determine the structure of a molecule, and inductively coupled plasma atomic emission spectroscopy is a spectral method used to determine very precisely so that's why we choose this title.
ఏంది కానీ స్పీకర్ వినిపిస్తలేదురా ఏమి మేడం వచ్చింది
Really to thank all the speakers for their generosity
ఓపెన్ చేసిర్రు
accepting our proposal to present the lecture without any honorarium, and I am greatly thankful to our professor NYS Murthy sir for arranging the speakers in such span of time. So now I would like to today one day national seminar Palamuru University PG College Department of MSc 5-year integrated chemistry organizes one day national webinar lecture series on spectral techniques. Today's speakers Usmania University, Dr. Raghu Chitta, Sir, Assistant Professor, Department of Chemistry, National Institute of Technology, Warangal, Professor Girija Mangatayar, Madam, former Registrar and Board of Studies, Chairman, Department of Chemistry, Palamuru University. I would like to webinar committee introduce Chief Patron Sri Rahul Bajja, IAS, In charge Vice Chancellor, Palamuru University, Patron Professor Pindi Pawan Kumar Sir, Registrar, Palamuru University, Chairman Dr. M. Nurjahan Madam, Principal University, PG College, and Advisory Committee, Dr. D. Madhusudan Reddy Sir, OSD to VC, Palamuru University, Professor P. Veerasomaya Sir, Dean, Faculty of Science, PU, Professor V. Leelavati Madam, Chairman, Board of Studies, Integrated Chemistry, Palamuru University, Dr. N. Chandrakiran, Assistant Professor, PU, Dr. S. Vijayalakshmi Ma'am, PU, Dr. A. Padmavati Madam, Assistant Professor, OU, Dr. G. Vijayalakshmi Madam, Assistant Professor, University College for Women, Koti, Dr. N. Navanita Madam, Assistant Professor, Saifabad, Dr. V. Chandrasekhar Sir, Associate Professor, Telangana University, Dr. S. N. Arjun Kumar, Placement Officer, Palamuru University, Professor NYS Murthy, retired, Palamuru University. Organizing Committee, Dr. K. Sridhar Sir, S. Ayesha Ashmi Madam, B. Upendra Sir, S. Ravikumar Sir, B. Siddharama Gaur Sir, A. Sudarshan Reddy Sir, M. Gyaneshwar Sir, and technical support, Gauss Moinuddin Sir, Department of Computer Science, Dr. M.S.R. Anjanel, PG Center, Kolhapur, G. Satyanarayana, Lab Assistants. Welcome you all, and finally participants. So now I would like to chief guest Principal University PG College, Dr. M. Nurjahan Madam. She completed 10 years of teaching experience and a research supervisor for DST Inspire program and mentored 4 DST scholars, presently 1 student pursuing PhD, about 11 research publications in reputed national and international journals, filed to now I would like to invite Palamuru University OSD2 VC sir, Dr. M. Madhusudan sir. He has vast 20 years of teaching experience. He worked as a research consultant at Global Institute of Biotechnology, Hyderabad. Now I would like to Palamuru University Register Professor Pindi Pawan Kumar sir. He is having 22 years of research experience and 11 years of teaching experience and Telangana Academy of Science District Coordinator. Welcome you all, sir. Now, welcome address by Principal University PG College, Dr. M. Nurjahan Madam. Please, Madam. Please wait for meeting host to be ready.
Good morning, all. Can you hear? Is it the voice audible? Hello.
Madam. Madam.
Hello.
Madam.
Hello. My voice is clear.
Yes, madam, your voice is clear.
Okay. Well, good morning, all. Welcome on behalf of Palamuru University to this one-day national lecture series, seminar and lecture series in spectral techniques, organized by Department of 5-year Integrated Chemistry. And I welcome Professor Jagadul Swami sir, former Registrar, Kakatiya University, senior most faculty member in the Telangana state. Namaste, sir. And welcome Dr. Madhusudan Reddy garu, OSD2 Vice Chancellor, Palamuru University. Professor Girja Madam, Chairman, BOS, Department of Chemistry and Pharma Registrar, and all the faculty members from various institutions, universities, colleges, research scholars, and my dear students. On behalf of Palamuru University, welcome you all to this webinar. On this webinar, it's I just want to, before starting, I just want to congratulate the organizing team, Ramhan, and faculty members of Department of Higher Integrated Chemistry initiative in organizing a webinar for the students, research scholars, because the title of this webinar is very much useful for the research scholars as well as the PG students and the UG students, because we are covering all the spectral techniques which are very, very important basic instrument and techniques for the structural elucidation or the identification of the compounds. So I think this is app for the curriculum which is there in the PG as well as for the research also. This technique are very much used for the structural identifications. And I thank Sir Jagannath Swami sir as a speaker for this seminar. Sir is a very well experienced, and he has extended cooperation right from the beginning, from the inception of the department. Uh, since 2009, we had a long cooperation from Professor Jagannath Swami sir. He has been always extending the cooperation, helping us in various symposia, seminars, by delivering the lectures and uh, and increasing our knowledge with his vast experience. And sir is a great teacher. And I welcome all the other speakers also who are from the eminent institutions like NIT Varangal and our Professor Gija Madam, very experienced teacher in the chemistry department. And we also welcome Professor Vigaru. He is also a good researcher from Usmania University. I extend my thanks and gratitude to all the officers as speakers have extended their cooperation and sparing their valuable time for our students and scholars. Thank you once again, sir. And this seminar is going to be helpful for all of us because these topics are useful for chemistry students. So I hope these lectures and the problems which are discussed and basic principles which are behind these techniques, they are very much useful to have the hands-on experience, because the theoretical concepts and the working principles one should know before understanding the problems. So if we could understand the concepts and the principles very well, then we can apply these principles and concepts in solving the problems which are used for the structural elucidation or the identification of compounds, organic compounds. Because nowadays the drug discovery and drug deliveries are very uh, important in today's scenario. In the corona situation, everybody are on the identification or in innovations of food drugs for the various infections which are overcome by the people in this world. So as a chemist, we should improve our technologies, or the spectral techniques really help us in solving these problems, and can be useful for our drug discovery and innovations in the near future, because all these scholars or students are the future scientists who are going to use these techniques and these principles in their future uh, works, and that can be useful. And we hope such lectures will improve your knowledge and really benefit you. And I thanks once again Professor Pindi Pavan sir for extending permissions and cooperation in conducting this webinars from the University College. And Professor Susan Reddy Garu, always they are cooperative and very helpful, and they always extend their cooperation in conducting the academic activities for the benefit of the students. And all the speakers, I once again extend my thanks to who share your knowledge with our students and faculty members. Thank you once again. Thank you, the convener of this webinar, Ramohan Garu, and the organizing team for giving me this opportunity. Thank you. Over to Ramohan. You can continue.
Thank you very much, madam, for your valuable suggestions to my department always as a principal and faculty of as a faculty member. Now I would like to inaugural address by Palamuru University OSD2 VC Dr. D. Madhusuran sir. Sir.
Hello. Hello.
Sir.
Yeah. Am I audible? Hello.
Sir, yeah, sir.
Yeah.
I listen, sir.
Thank you, Ramon, sir. Very good morning to one and all. Professor Jagannath Swami, sir, former registrar Kakatiya University, and sir was, behind our establishment of our Department of Chemistry when our founder, Vice Chancellor, Professor V. Gopal Reddy Garu has established the department. So we used to have a very good rapport with sir. Sir has helped us in all the ways. So where the department has brought many laurels to our university. So thank you, sir, for once again for your cooperation. Professor Vittal, sir, retired professor from Usmania University. Professor Girja ma'am, former registrar and chairman board of studies, Department of Chemistry, Palamuru University. Professor, Dr. Raghu, sir, assistant professor from NIT, and my dear faculty members of Integrated Chemistry, Department of Integrated Chemistry, Palamuru University, and other lecturers and research scholars and students. Good morning to one and all. So on behalf of our Honorable Vice Chancellor, Sri Rahul Boja, IAS Garu, and the respected Registrar, Professor Pindi Pawan Kumar Garu. So I congratulate the Department of Integrated Chemistry. So having arranged such a wonderful lecture series on spectral techniques, and I really appreciate our principal, Dr. Nuja ma'am, who has taken and who has led the department for conducting such a wonderful, taking initiation for conducting such wonderful lecture series. And with regard to the topic, we know the importance of spectral techniques, where this technique will span into all the areas, right from my department, microbiology, biochemistry, astronomy, chemistry, into every field. So it has got a very significant part where whenever you want to detect quality-wise or quantity-wise any compound, chemical compound, right? So these compounds are these techniques are very much useful, whether it is atomic absorption spectroscopy, atomic emission spectroscopy, IR, infrared, near IR or far IR, UV spectroscopy, NMR spectroscopy. All these techniques actually they play a vital role. And recently, when I was just going through the latest techniques of these spectral techniques actually. So I came to know that this Massachusetts Institute of Technology, in association with Samsung Institute of Technology, they have identified, they have found out a new method for detecting blood sugar levels. Till today, what we are doing is we are going through an invasive technique where you need to prick the finger and take the blood sample and find out the amount of blood present in the blood sample. But they have identified using a far infrared technique, where without pricking the finger, you can detect the blood glucose levels. Actually, really, it's a good technique. So that's why such techniques, so where it can really come down to common man. So they are really appreciated. So we have actually these techniques where it has proved the expansion of galaxy system. So it has proved its importance in medical diagnostics, in identifying compounds, whether they are in very minor quantities like parts per million concentration also, right? So especially for research scholars, when they give a compound for identifying their compound, their structure, their molecular weight and all, we know how much eagerly they will be waiting, when it comes to taking the results of NMR, proton NMR of all these things, right? So really, even I am eagerly waiting to listen to Professor Jagannath Swami sir, Professor Vittal sir, Professor Girja ma'am, and Raghu sir, because even such techniques are helpful for our field also. And I once again congratulate the Department of Integrated Chemistry for arranging such wonderful lecture series. Thank you, Ananda. Thank you.
ఏసీ నీళ్ళని కారుతున్నాయండి. ఏసీ నీళ్ళు మొత్తం కారుతున్నాయి, జారిపడే.
Ramon sir. Hello.
Thank you very much, sir, for your kind cooperation to the department as well as your valuable message in this webinar. Thank you so much, sir.
Okay.
Now I would like to introduce Professor S. Jagannatha Swami sir by Mr. B. Upender sir, faculty, Department of Chemistry.
Good morning to all. Let me introduce Professor S. Jagannath Swami, sir, to this webinar of integrated chemistry. Sir is a recipient of a Best Teacher Award from the government of Andhra Pradesh, has a vast experience of teaching chemistry at 10+2 undergraduate and postgraduate levels, and pin video. And sir has did postdoctoral research in University of Technology Berlin, Federal Republic of Germany. Sir has published research articles in reputed journals of chemistry. Under his valuable guidance, 16 scholars received PhD degrees. And sir, in addition to these academic activities, sir is the former registrar of Kakati University and HOD of Department of Chemistry. And he successfully completed 7 research projects of UGC and DST and DRDO. Next, sir is a Dean, College of Development Council, Dean, Faculty of Sciences. He was on the Board of Studies of Chemistry of Kakatiya and other universities. Professor Swami earlier published 3 chemistry practical manuals for the degree students of Kakatiya University during 1990s. He is a prolific writer on contemporary issues of higher education in newspapers. With this brief introductions, I request to deliver Professor Jagannath Swami sir to deliver a lecture on this webinar. Thank you, sir.
Good morning, sir.
Good morning.
Professor S. Jagannathan Swami sir, lecture on UV spectroscopy. Sir,
Okay.
please, sir.
Yeah. Are you able to hear me?
Yes, sir.
Okay. Good morning, everybody. Thank you very much for inviting me to deliver this lecture on webinar for 5-year integrated MSc chemistry students. I am very happy because after a long time I am coming into contact with the faculty members and students of Palamuru University. Actually, I was very much associated with this university during the period of Professor Gopal Reddy Garu as Vice Chancellor. Without taking much time, I start the lecture. I'm going for sharing screen. Okay. Everybody hearing clearly me?
Yes, sir.
Yes, sir.
Yeah, my topic is on a part of spectroscopy. As you are seeing a flag on the screen, it consists of several colors, starting from violet at the bottom to the red on the top. Now, this is actually the spectrum of white light. The spectrum is a very common word for scientific community, but also everybody knows about spectrum. That we see later. What is spectroscopy and how is it useful to the science students? As some of the speakers have mentioned about the importance of spectroscopy, I deal with one aspect of spectroscopy, that is UV visible spectroscopy and its applications. Spectroscopy can be simply defined as seeing the unseeable. Seeing the unseeable. That which we cannot see with our naked eyes, but we can see for example, if somebody closes your eyes, ties with a cloth, and then puts a cylindrical like object in your hands and try to identify it. By closing your eyes without seeing it, you have to identify. How do you do it? You touch it. You touch the whole length of the body, say about 8 inches or 9 inches. What do you feel? You feel it as a soft and very.
Sir, excuse me, sir. Excuse me, sir. We are unable to see the screen.
You are unable to see the screen. I am already
Yes,
sharing
sir.
it.
Actually, we are unable to see the screen, sir.
1 minute, 1 minute.
Yes.
అయిపోయిందా బాబు చాలే ఏమైంది
Now, how is this?
Now you are visible, sir. You are visible.
How about the screen?
Screen we are unable to see, sir. Still.
1 minute, 1 minute. I have already opened it. Zoom. Okay, I'll show this way. Now.
Yes. Now we are able to see, sir.
Okay, thank you.
Yes, sir.
Then I'll continue.
Yes.
Okay.
Yes, sir.
Spectroscopy is seeing the unseeable. I'll continue from where I stopped. Yeah, you are holding that object in your hands and you just feel the smoothness of this and you feel that it is soft. And as you move your hands over the object, you find somewhere it is torn and you feel it, you remove it. Then you will able to completely remove the peel. And then what you do is with your nail, you remove a small part of it and take it to your nose, try to smell it. And then if your smell is pleasant, you try to taste it. Okay. So by tasting, by smelling, and you will come to a conclusion that it is a fruit. Now, what part of body tells that it is a fruit? That is brain. The brain with its data previously stored in it, it will automatically tell you that it is sweet and a fruit. Okay. So like that, even in the spectroscopy also, we use the same, our senses, our memory, and other aspects to confirm things which are not seeable. So this is the beauty of the spectroscopy. Using electromagnetic radiation as the probe to, can I
Sir, audio off అయింది sir. Audio.
Now is okay?
Yes, yes. Now it
Okay,
is.
sir.
Okay. What is electromagnetic radiation? I'm unable to run this. Yeah. Using electromagnetic radiation as a proof to obtain information about atoms and molecules are too small to see. Electromagnetic radiation is propagated at the speed of light through a vacuum as an oscillating wave. You just note down this last part, oscillating wave. That is, radiation propagates in an oscillating wave motion. Electromagnetic radiation is a form of energy exhibiting wave-like behavior as it travels through space. Electromagnetic radiation. Now, from this word itself, you know there is a electrical component and magnetic component in the electromagnetic radiation. Now, just you watch this. Here, the light is propagating from left side to the right side, left side to the right side, and there are two arrows, one blue colored and the other orange colored. Blue colored radius are perpendicular to the propagation, way of propagation, and orange arrows are perpendicular to the propagate radiation, but they are parallel to the x-axis. So these two arrows are perpendicular to each other and perpendicular to the way of propagation. The one in the vertical arrows indicate the electrical component, and those in the orange or horizontal indicate the magnetic. So like that, electromagnetic radiation is the mixture of these two. Whatever properties we observe, whatever effects the light makes on the body or matter, or the result of the interaction of these electric and magnetic components with the matter. Electromagnetic waves can be imagined as self-propagating transverse oscillating wave electric and magnetic fields. This diagram shows a plane linearly polarized wave propagating from left to right, as I mentioned. The electric field is in a vertical plane and the magnetic field in the horizontal plane, like that. Now you see, this is a very common feature we come across in the nature. Whenever it rains or near the waterfalls, we often see this bow shaped color band, which we call it as rainbow. Rainbow is nothing but the spectrum of white light. A spectrum is the division of the electromagnetic radiation, and this consists of different colors. That is natural phenomena, and in the laboratory, artificially we can also get the spectrum of white light using a simple gadget like a prism. Just allow the white light to fall on the prism, and hold a paper on the other side of the prism. You will find the colors. You will find the colors as you observe in the case of the electromagnetic radiation in the nature, that is rainbow. So like that, we can analyze the white light and get the spectrum of the white light. You see, the white light consists of the 7 colors: Vibgya, blue. In between Vibgya and blue, indigo comes. Blue, green, yellow, orange, and red. So this is the 7 colors. This is the artistic. Suppose if we rotate this with a very high speed, what happens? Just you see this. The wheel is rotated in this direction at a faster rate, and all the 7 colors mix up, and our eyes cannot see all the colors individually, but that looks like white. So like that we can say The white light is the mixture of 7 colors. And using this, we can show the properties of
అదేం బుక్ టీవీ ఫైల్
the properties of light are very important in understanding the interaction of the white light with the matter. The properties of light are wavelength, that is lambda, that is indicated by the distance between the successive crests or successive troughs, and energy of radiation, and velocity of radiation, and frequency of radiation. These are the properties. We can differentiate one part of light with the other by using these properties. Properties are lambda, wavelength, frequency, and velocity of light, and energy of light. And in all these cases, we use one constant, that is Planck's constant. Lambda wavelength, c speed of light, h Planck's constant, frequency mu, and kinetic energy E. Kinetic energy because the waves are always passing through. They possess kinetic energy. And the different relations are lambda into frequency is equal to c velocity of light, E is equal to h into nu, and this can also be given as E is equal to hc by lambda. This is because nu is equal to c by lambda. As we see here in the equation, E is equal to h nu, then E can also be given as h into c by lambda. Mu is equal to c by lambda. Lambda is inversely proportional to frequency. Energy is proportional to frequency, and energy is inversely proportional to wavelength. All these relations are very important. Any student of science must remember, all students of science should remember these equations, because we use these equations depending on our requirement. And you see the light energy, as I mentioned, is not just white light what we see, but there are other radiations which we cannot see with our naked eyes. Say the radiation is differentiated into one another from its frequency, changing from 10 to the power of 0, that is 10 to as 1 to 10 to the power of 24. Frequency is increasing. As you know, as the frequency increases, the energy of radiation also increases. These are the long radio waves, these are the gamma rays. Energy of long radio waves is less, and as you move to left, that is high frequency side, the energy goes on increasing. It's very important because the matter. There's a lot of disturbance. And you see here at the bottom, we find wavelength ranges from to 10 to the power of minus 16. Wavelength is decreasing and the frequency increases. And long range radio waves, AM radio waves, these are which are used for transmitting radio waves, and FM, microwave, IR, infrared radiation. This is visible part colored, and ultraviolet, X-rays, and gamma rays. Like that. But a very small portion of the radiation is visible to our naked eyes. That is, our naked eyes can recognize them. This is visible radiation. And in the visible radiation here, from IR at the extreme right hand side, longer wavelength, and at the left side, extreme left side, ultraviolet, that is, the wavelength is less than 400 nanometers. And we can see the different colors and associated wavelengths and the property of the light. Ultraviolet ranges from 190 to 400 nanometers, and we cannot see these lights. we cannot see this light. Ultraviolet radiation is not visible because the frequency is so high, our eyes cannot detect it. Violet 400 to 420, indigo 420 to 440, blue 440 to 490, green 490 to 570, and yellow from 570 to 585, orange 585 to 620, and red 620 to 780. So like that, different radiations are useful for our study of the matter. How is this electromagnetic radiation is useful for students of chemistry or for all students of science? The interaction of matter with energy. The simple form of energy and the one which is responsible for growth of the human civilization from rock age to present age. So the energy is very, very important for prosperity of the human civilization. And where from we have started? We started from the time of discovering heat, thermal energy. That is, heat, thermal energy is very important. What happens when matter is heated? Heating means we are supplying energy in the form of heat. We are supplying energy in the form of heat. It's a simple example everyone can understand. We take ice and go on heating it. What happens? We can see the changes visually. That is, ice on heating, it becomes liquid, that is water, and on further heating, the water becomes vapor, that is water starts boiling and vapor comes out. Whether it is in the form of ice, solid, water, liquid, or vapor gaseous state, the chemical composition is same, that is H2O. So, but there is a physical change in the matter. And this, just see this picture. Here in the beaker, I have taken some ice pieces and started heating it by immersing a thermometer in it. Now, initially, before heating, the temperature records at 0 degrees Celsius, that is the melting point of water. And then, as you go on increasing, the ice melts and the water we get. And the mercury column in the thermometer goes on increasing. Yes, as we heat the water, that is the material in the beaker, absorbs energy, changes its physical state. And you see, after heating for some more time, the water starts boiling. And here this is vapor. So the water vaporizes and the temperature increases to a certain level. And on continuation further, yes, the water still boils and mercury column, even though we are heating, it doesn't rise, it stops there. All these changes we can see by just carrying out this simple experiment. Now, what happens to the energy that is we are giving here? That is used as latent heat of vaporization, that is only for changing the physical state, but there will not be any increase in the temperature. The matter absorbs thermal energy and under circumstances in the physical state. Yes. Thermal energy is continuously absorbed, and this can also be used for some other purposes, not only bringing about physical changes, but also for chemical changes. There is a lot of disturbance. Ramahan, hello? Yes, you see this. Here we are using a benzyl chloride and heating in presence of alkaline potassium permanganate. And after heating for some time, you pour it in water, you will get a white crystalline solid, that is benzoic acid. So here we have used thermal energy shown in the form of this, and we get the benzyl chloride converted to benzoic acid. Similarly, the calcium carbonate on heating dissociates to give calcium oxide and carbon dioxide. When the matter is heated to high temperatures, it decomposes. Now you see this diagram. The small diagram. Yes. What is chemical reaction? Okay, are you able to hear me?
Yes, sir.
Okay. Now the chemical reaction is the breaking of bond or formation of bond. What happened?
Sir, continue, sir.
Light energy and its applications. This is the actual part of our lecture. What I have given is the introduction about light. Its two components, magnetic and wave, sorry, electrical. And actually, whatever changes we observe by the interaction of light with matter is just by this electrical as well as magnetic field component interaction. They import something to the matter in the form of electrical energy or magnetic energy, and these energies bring about change in the again the same different forms of radiation, and depending on the sizes starting from the smallest sized article, that is water molecule, to the soccer field, that is football field, to the larger side, that is the size of a wavelength, everything like that. And these are the different applications we use. radio that is the radio waves, and this is x-rays. So like that we go on applying the application goes on changing with the properties of the light. Now why should we study this ultraviolet spectroscopy or visible spectroscopy at this particular time? At this particular time, because we have a variety of analytical techniques at the hand of the scientists, and they give more useful information about the structure of the matter and finer details of the matter. But still, why do we use this ultraviolet spectroscopy? This is because many organic molecules, of course inorganic compounds also, have chromophores that absorb UV or visible radiation. Because the matter is having such color giving substances, by exploring those, we can understand something about the matter. UV absorbance is about 1000 times easier to detect. Now, what technique we select is dependent on how easily we get the information. The UV absorbance is about 1000 times easier to detect for more than NMR. It means UV spectroscopy is more sensitive and more reliable, more sensitive and more reliable than NMR. So another important point is cost factor. Yes, UV spectrophotometer, even a better spectrophotometer we get for 4 to 5 lakh rupees. But for going for a moderate NMR spectrophotometer, we have to spend at least 2 crore rupees. This much amount is not available to all labs. So therefore, this UV spectroscopy is simple, fast, and economic. So therefore, many labs use this for primary investigations of the matter. Still use it in following reactions where chromophores change. Useful because time scale is so fast and sensitivity is so high. Kinetics, especially biochemistry and enzymology, can be easily followed using UV spectroscopy. Most quantitative analytical chemistry in organic chemistry, that is in analytical chemistry, we use separations and detection by HPLC, and these HPLC high performance liquid chromatographs use UV detectors. One wavelength may not be the best for all compounds in a mixture, but HPLC are very high. ఎవరికైనా చెప్పేది Okay, able to hear me? Okay. So here what is the nature of the light? We have seen one part of the light that is in the form of wave. It oscillates in the form of wave. But to describe the properties of light, we need to have another theory. That theory is the particle phenomena. That is, light consists of both wave nature as well as particle nature. Okay. Again, what happened? The screen. Ramon, you did something. I'm unable to.
Sir, screen కనిపిస్తుంది సార్ లైట్ పార్టికల్స్ అండ్ వేవ్స్.
That's okay, but yeah.
Okay.
Yeah. Other way of representing light is wave phenomena. I just see the properties of light energy we have seen in the form of lambda, frequency, energy, etc. And when you describe the light in the form of particle, you apply particle nature to the light, then the same properties of light must be able to be explained in the form of particle theory also. So that we see here. How does matter interact? As here, this is sun. Are you able to see the pointer? Are you able to see the pointer? I am using pointer also. No? Okay.
Yes, sir. Yes, sir.
Okay. So this light, that is a source of light is the sun, and how the matter interacts with the sunlight or the light energy. Just I try to explain 3 different ways. 1, 2, 3. Okay. Here in this, the light energy falls on the object, and this object is having such a property that it doesn't absorb any light, but it reflects all the light that is falling on it. Say the white light means, as we have seen, it is a mixture of 7 colors. All 7 colors are falling on the body, and all are reflected back. All are reflected back means white light is being reflected here. Okay. It means this white light reaches our eyes, and that will be the color of the object. So the objects looking white will not absorb any part of light, and they transmit or reflect all radiation that is incident on it. Other type of how they completely absorb radiation. The light falling on that is completely absorbed, and as a result of this, we can't see any radiation being reflected from this object. So all light is absorbed. So automatically that object looks like black. And suppose if other object absorbs a part of incident radiation, this is incident radiation, this is transmitted radiation. If it absorbs a part of incident radiation, that part is absorbed and the remaining colors are transmitted. A part of the light is absorbed, the remaining light is transmitted, and the object will look with a complementary color. So like that, this is how the matter interacts with light, and this gives a simple information about the matter. What is that? The first matter is white in color, the second one is black in color, and the others will have a definite color depending on the light absorbed and light transmitted. The next slide gives you about the energy, that is H is equal to H nu. The main difference between the absorption or interaction of matter with thermal energy and light energy. We have already seen how thermal energy absorbed. It is continuously absorbed. Say in the case of water, starting from 0 degrees to 100 degrees Celsius, the thermometer mercury column raises continuously without any gaps. Thermal energy is absorbed continuously, while light energy is absorbed in specific quanta. This is very important for application of light energy in our investigations regarding matter. The light energy is absorbed in specific quanta is very important in using the light energy for getting the structural information of the molecules. So what are the different types of energies associated with the molecules? That is, E total is total energy of the molecule. that is equal to E translational, E electric, electronic, E vibrational, E rotational, E nuclear. So the total energy of the molecule is the sum of all these forms of energy. Translational, this is because the molecules continuously move in the gaseous state or liquid state, in the fluid state. Okay? But still the atoms and molecules will be continuously vibrating. So vibrational energy, electrical energy, and rotational energy, because the molecules will be continuously rotating, and the nuclear energy. So these are the energies associated with the molecule, and the total energy is the sum of all these forms of energy. Now actually what happens when the light energy falls on the objects? The spectroscopic process involves, especially in UV spectroscopy, the sample is irradiated with the broad spectrum of UV radiation. We allow the light to fall on the matter. If a particular electronic transition matches the energy of a certain band of UV, it is observed. Here, this particular point is important. That is, particular energy transition matches. It means the energy associated with the light and the energy difference between the different bands is very important for the light to be absorbed. It is not like thermal energy to be continuously absorbed, but it is absorbed in packets. The remaining UV light passes through the sample and is absorbed. From this residual radiation, a spectrum is obtained. That is actually spectrum is in this particular case. In this particular case, we record the radiation that is transmitted by the body and we get information about that. From this residual radiation, spectrum is obtained with gaps at the discrete energy level, and we call this as absorption spectrum. Spectra is of two different types, that is absorption spectrum and emission spectrum. Of course, here concerning UV and visible, we just deal with the UV, absorption spectrum. Now, how do we describe the energy levels in the molecules? This is very important. Unless we understand about the energy levels associated with a molecule or atoms, very difficult to interpret the spectrum. Okay. Now, further, in the case of molecules, I am not talking about atoms now, but just molecules. Atoms phenomena is same, but it's slightly different. In the case of molecules, we describe the formation of the molecule by the formation of a bond. Now, formation of bond can be described by different theories, starting from valence bond theory to the molecular orbital theory. So, molecular orbital theory helps us in understanding the different energy levels associated with the molecule. Yes, the atomic orbitals mix up and redistribute themselves into the molecular orbitals. Say this is an atomic orbital and this is another. They combine, they mix, and they give rise to two types of bonds. I am giving a simple picture indicating the lowest energy orbital is pi orbital and high energy orbital is pi star orbital. Okay, and what happens here in a stable molecule, the two electrons stay or occupy the lower energy state always. Any stable molecule will have electrons in lower energy states. Okay, and we are irradiating the sample with light. Okay? This is light energy. And on irradiation, what happens? This absorption energy. If the radiation or the energy associated with light matches this energy gap between pi and pi star orbitals, that energy is absorbed, and this energy makes one of the electrons jump from lower energy state to the higher energy state, like that. From lower energy state to the higher energy state. So like that, that makes the light energy to higher energy state. Yeah. The relation between absorbed and observed energy. Just you see difference between these two words, absorbed and observed. This observed is nothing but complementary color. Actually, the color of the object. Say, for example, any matter absorbs violet radiation. Line close. Violet light is 400. That light is absorbed, and transmitted radiation is more in 560, more in nature of 560 nanometers wavelength, and it is greenish yellow color. Any object that absorbs violet color will look green. If an object absorbs blue light, that is 450 nanometers, it looks yellow. The 600 nanometers is the wavelength of the radiation transmitted. So like that we give. And these are the different energy levels of the molecule. In the last slide, I have shown only two, but actually how many? Now we are concerned with organic molecules. I want to, in this part, I am not touching D block elements or inorganic compounds, only organic compounds. So organic molecules are formed by the bonds by involving only two types of orbitals, s orbitals and p orbitals. Organic molecules, carbon compounds, they have only s and p orbitals, no d orbitals. So how many types of orbitals are formed by the linear combination of atomic orbitals, LCAO? Molecular orbital theory is mainly developed using this proposition of LCAO, linear combination of atomic orbitals. And by combining the different orbitals using their symmetry properties, energies, etc., we get so many types of molecular orbitals. Sigma bonding orbital, sigma anti-bonding orbital, pi bonding orbital, pi anti-bonding orbital, and non-bonding orbital. These non-bonding orbitals don't change their energy, and sigma bonding orbitals, low energy, high energy, sigma and sigma star, pi bonding, low energy, pi anti-bonding, pi star. So like that, these are the molecular orbitals. And electrons reside in these orbitals. Electrons reside in these orbitals. If the molecule is said to be stable, then all electrons will be distributed. All electrons will be distributed in the sigma or pi or non-bonding. If the electron density increases in pi star and sigma star orbital, the stability of the molecule decreases. Now, when we supply energy to the molecules, some changes take place, as we have seen in the previous slide. What happens? Depending on the energy associated with the light, the electrons transmit from one energy level to the other energy level. Now, depending on the energy associated with the light energy. So now you see here, the different possibilities are bonding orbital energy. If energy supplied is more, so electron from sigma bonding orbital jumps into sigma star orbital. This transition is called sigma to sigma star. And if the energy is not that much but less, but equal to the energy difference between this pi star orbital and this pi orbital, then electron transition takes place from pi to pi star and n to sigma star and n to pi star. All these are the possible transitions when a light energy falls on the organic molecules. Like that. Sigma to sigma star, pi to pi star, n to pi star, n to sigma star. These are the transitions. Now, where do we find, in which type of molecules we find this type of transitions? The sigma to sigma star transition, because they are saturated molecules, they have only sigma bonds, all sigma bonds, and alkanes. Such compounds are alkanes. Alkanes exhibit sigma to sigma star, and carbonyl compounds, sigma to pi star, because pi bond is there, carbon oxygen double bond, pi star, sigma to pi star in carbonyls. Unsaturated compounds, they give pi bonds and pi to pi star transition, and n to sigma star in the compounds containing oxygen, nitrogen, sulfur, and halogens, which have non-bonding pairs of electrons on the atoms, and N2 pi star in carbonyls, because they have lone pair of electrons on nitrogen and pi bonding and pi antibonding orbitals of the bond and transition. So like that, now you see, by identifying the transitions in the molecule, we can say whether a molecule is an alkene or a carbonyl or an unsaturated compound or compound containing oxygen, nitrogen, halogens or carbonyls. So like that, the information about the molecules can be obtained using the electronic transitions. Electronic transitions are recorded or observed by using the UV or visible spectrophotometer. Now the UV region extends even below 100 degrees, from below 400 nanometers starts and even below 100 degrees, 100 nanometers. But the problem with this radiation is the oxygen in the air is not transparent to the ultraviolet radiation whose wavelength is less than 200 nanometers. If you allow such radiation to fall on the air, then air absorbs all that, oxygen absorbs all the ultraviolet radiation, and we don't get don't get any information about the molecule absorbing below 200 degrees. So what do we do? For recording such spectra below 200 nanometers, we have to use an improved version of the instrument that is called as vacuum or far ultraviolet spectrometer. There should be some provision for evacuating the complete chamber and removing oxygen. The routine ultraviolet spectra of organic compounds are typically recorded or collected between 200 and 700 nanometers. Say what type of absorptions we can find in the UV spectrum of organic compounds. That is sigma to sigma star in alkenes, sigma to pi star in carbonyls, pi to pi star in unsaturated compounds, N to pi star in compounds containing oxygen, nitrogen, sulfur, and N2 pi star in carbonyl compounds. Now in these 5 types of transitions, I have shown these unsaturated compounds pi to pi star and N to pi star a bit dark, and others are not very light. It shows that these absorptions are not frequently observed. In simple molecules, these transitions are not observed. So you should remember that. This is because sigma to sigma star transition leads to the breakage of the bond. When electron density in the antibonding orbital increases, the bond breaks. So this leads to breakage of the bond, and as far as the UV spectrum is concerned, these transitions are least important. They are not important for us because they don't give. By the time we record the spectrum, the bond breaks. And the carbonyl compounds also, they are not observable because they are around 170 nanometers, falls in the far ultraviolet region. Ions that are possible to be observed. 1 minute. This is giving trouble. Can you remove this window?
Sir.
So get this window. This line is coming in my way. Okay, sorry. Not all transitions that are possible are observed in the spectrum. Whatever transitions are possible in the molecule, all may not be observed. For an electron transition, certain quantum mechanical constants apply. These are called selection rules. So for a particular transition to be observed, that transition should follow certain rules, and these rules we call them as selection rules. Selection rules are very important in interpretation of the spectrum or in using the spectrum for saying something about the structure of the molecule. For example, an electron cannot change its spin quantum number. The most important is the spin quantum number should not change. That is, before transition and after transition, the spin state of the molecule should be same. If there is a change in the spin state, that transition is forbidden. These are called forbidden transitions, and these forbidden transitions are not often observed. I don't say that they are not observed, but often they are not observed. Under certain conditions, yes, we can see the forbidden transition also. We see those conditions later. The number of electrons that can be excited at a time is one. Only one electron can jump at a time, not more than. Symmetry of the properties of the molecules also determine the state of transition. Symmetry of the electronic state is very important, and this is a little bit complicated. So I do not want to go into this in detail because we should have a complete information about the symmetry properties of the molecules. I think second year, third year students may not follow this symmetry properties of orbitals, etc. And the further to further complicate can you remove this window? The small bar is seeing. Okay. To further complicate matters, forbidden transitions are sometimes observed. As I just mentioned, the forbidden transitions are also observed, but albeit at low intensity. Intensity is very less due to other factors, some other factors. But sometimes these forbidden transitions also give useful information about the molecule. Band structure of the molecules. Unlike IR, and later we see, I think Professor Witter will deal with this IR spectroscopy. Unlike IR and later NMR, I think Professor Girja will discuss this NMR. In these two cases, we find very sharp lines in the spectrum, where there are maybe upwards of 5 or more resolvable peaks from which to elicit structural information is easy and more. But UV tends to give wide and overlapping bands, as we see in one of the spectrum ladder. It would seem that since the electronic energy levels of a pure sample of molecule would be quantized, this is very important word, quantized. Quantized means associated with a fixed amount of energy. So these electronic energy levels are quantized. The discrete bands would be observed for atomic spectra. In the atomic spectra, sharp lines are observed because the energy gaps are very fixed and electron jumps from this to this, unlike the ultraviolet spectrum of molecules. The molecules is slightly different, we see in the next slide. In molecules, when bulk sample of molecules is observed, not all bands are in the same vibrational rotation energy that we see in the diagram. Next slide. Okay. Now you see this diagram. Here we try to understand why the UV spectral lines are very broad. UV spectral lines are very broad, something like that. Now just you try to understand. This is the very, very important point in observing, in understanding this. Now this consists of the molecule energy levels. These are the energy levels of the molecule. So molecule will have different energy levels. Energy levels, say electronic energy level shown in blue, and this is next higher energy level, E prime. E0 ground state and E prime is next higher energy level. But the molecules are having other types of energy, as we have seen the equation E total. It is having rotational as well as vibrational. Of course. Now, these orange color lines in this indicate vibrational energy levels, and these violet color lights rotational energy levels. Okay. Yes, we take a molecule in the ground state. That is, we don't supply energy except that of the surroundings, because we are keeping the molecule here in the room means always thermal energy is supplied to that. Okay. So now we are taking a sample means it is not one molecule, but it is several hundreds or thousands of molecules are there in the sample. Okay. Now the molecules will be there in the ground state because the molecule is compound is stable. But even in the ground electronic level, some molecules may be in this vibrational energy, some in the vibrational energy, some in this vibrational energy. Electronically, they belong to same energy level, but vibrationally, they are in different energy level. Similarly, some molecules may be in a given vibration energy in this rotational, in this rotational, in this rotational, in this rotational. So the rotation energy level changes. So the molecules may be in any of these energy levels, either vibrational, rotational, in a given electronic energy level. Okay, that is the state of molecules, different molecules in the ground state. And I supply energy, light energy to the molecule. Then a molecule in this electronic level and zero vibrational and zero rotational. Okay, when I consider this molecule here in this blue level, yes, this absorbs energy and goes to this level. If only that thing happens, we get only one sharp line. If electron jumps from this level to this level, only sharp line. But it is quite possible that molecules from this rotation level may jump to this rotation level, this rotation, because energy associated with the rotational energy levels is very, very small. So like that, molecules in different vibrational and rotational energy levels absorb energy and go to are excited to different vibrational rotation levels. It means all these are possible in a single stroke. In a single stroke, all these transitions are possible from one electronic energy level to other electronic energy level, but of different vibrational and rotational levels. And you should understand that the energy associated with each of these absorption is slightly different. And in the spectrum, all of them lie just one side, side by side. So all these side by side bands are observed, and that takes a broad structure, as you see here. So the same diagram shown in a different way, giving the indications. How do we represent the spectrum? The spectrum consists of two axes. Because we are drawing it in two-dimensional paper, it consists of two axes, x-axis and y-axis. On the x-axis of the spectrum, the wavelengths are written 200 to 350 from UV region and 200 to 700 in the UV visible spectrum. Okay, and the y-axis we will give the optical density. That is how much radiation is absorbed. Okay, the Beers-Lambert's law tells all about that. And then this is the spectrum of a molecule. A typical molecule 3 amino 1 benzofuran 2 while phenyl ethanol. So this is the structure of the molecule, and this molecule gives this UV spectrum. Now you see these bands, broad. This is very broad band, something like that. Whereas in the case of IR spectrum, you will find very sharp lines like that. And in the case of NMR spectrum, just lines like that you find. They are very, very sharp. So here these broad absorptions are seen because the light energy absorbed or transmitted will be just like that, side by side. Just so from this region to this region, several lakhs of radiations, lights will be there, and they are clubbed together and give this broad structure to this electronic absorption. And in such cases, what we do, how to present this broad will not give correct information. So actually we take the lambda maximum, peak of each of the line. They are starting from 206, 252, 317 and 376. These are the characteristic absorptions of the compound 3 amino 1 benzofuran 2 while phenyl ethanol. So like that, these peaks correspond to the molecule. So like that we present electronic spectrum of molecules. Now we go to the summary and then applications. Ultraviolet visible spectroscopy from 200 to 400 and visible from 400 to 800 correspond to electronic excitation energies of molecules. In particular, transitions involving pi orbitals and lone pairs are very important because the others may be forbidden or not observed. So these are the transitions that are characteristic of a large number of organic molecules and give information about the structures of the organic molecules. The lowest energy transition is that between the highest occupied molecular orbitals HOMO, highest occupied molecular orbitals HOMO, to lowest unoccupied molecular orbitals. These are unoccupied but high energy. These are occupied but low energy. So electronic transition from this to this indicates the absorption of light and gives a band in the spectrum, and observing this band will tell about the energy levels present in the molecule. The absorption of electromagnetic radiation excites an electron to the LUMO from HOMO, and the molecule goes to excited state. The more highly conjugated systems, the smaller the HOMO-LUMO gap, and delta I is less, automatically wavelength is longer, that we see in the examples. And the colors we see in inks, dyes, flowers, etc. are due to highly conjugated organic molecules. The unit of the molecule that is responsible for the absorption is called the chromophore. That is the functional group in the molecule that results in the absorption of radiation. Something like the C double bond C that results in pi to pi star transition, or C double bond O results in N to pi star transition. These groups present in the molecule are called chromophores. So the chromophores are responsible for absorption of light energy. Now we see something about the spectrophotometer, how the spectrophotometers are developed. Now first we discuss something about, or try to understand about natural spectrophotometer. In the natural spectrophotometer, sun is the source of radiation. Sun always transmits energy 24 hours and 365 days. 24 hours and 365 days. And that light energy is made to fall on the object, a chemical matter that falls on the matter. And this substance absorbs a part of radiation and transmits the unabsorbed part of light, something like that. All 7 colors are for reaching the molecules, and molecule absorbs a part of light and then transmits the other. And this absorbed radiation goes to our eyes. Actually, we see. So what is the detector in the natural spectrophotometer? That is our eye. Just we see. I think. And then that eye sends the signals to, eye sends signal to the brain. Yes. Whatever we see, how do we recognize? We recognize when the sense organs send the signals to the brain, and brain is having all the information stored in from our previous experiences and from whatever we have studied and whatever we are taught. Yes, the brain keeps in it. That is the database for the, and from the eye signals reach the brain, and brain analyzes and detects what it is. If you are given with a pink solution, automatically a student of chemistry says that it is potassium permanganate solution. If a blue solution is given, you say it is copper sulfate solution, something like that. A green solution is given, you say it is nickel chloride or nickel sulfate solution. So like that, the information stored in the brain is useful in identifying what it is. Now what we are using in this, we are using the sunlight, allowing the light to fall on the object. Object absorbs and transmits. Transmitted radiation reaches eye, and that sends signals to brain, and brain detects. So these are the processes that take place in a natural spectrophotometer. Based on these processes, the human beings artificially developed the spectrophotometers, the man-made spectrophotometer. Now, what are they here? What are the components in the man-made spectrophotometer? Yes, it is source of light. Generally, we use electric bulbs. Nowadays, we are using LED bulbs also in the spectrophotometers. And the spectrophotometers also, the source also transmits all white color radiation. Yes, and here the man made some improvements compared to the nature. That improvement is the 7-color radiation that is reaching is made to fall on an object. This object is called prism. In a simple colorimeters we use prism, but in more sophisticated instruments we use gratings. So the prisms or gratings are used, and what they do, they transmit only one part of radiation. That is, other radiations, all other colors are filtered and transmits only one radiation. If you want a different color, just simply rotate the prism. Rotate the prism, another color is allowed to pass through the slit. So like that we have a monochromator, and filtered radiation is allowed to reach the sample. Yes, sample. And not all radiations are reaching, but only selected wavelength radiation reaches the sample. And then from the sample, radiation is transmitted, and transmitted radiation reaches a detector. Just like here, the detector is eye, and here we use a electronic component, a detector. Detector detects this light. On what basis? Based on its frequency, based on its wavelength. So it detects that and sends it to the analyzer, that is the brain. And brain analyzes it, and what radiation is reaching that particular detector, and then it gives in the form of a spectrum. So like that, this is the man-made spectrum. This is the man-made spectrum consisting of the different component source of light, monochromator, that sample, detector, analyzer, and recorder. So like that we get the spectrum, and these are the main components of any spectrophotometer. Maybe here is ultraviolet or IR or NMR or any other thing. These are the main components. And this is the spectrophotometer we see in the lab, and this is how they function. And these are the sources of light. So this is the tungsten filament for visible radiation. This is the halogen, hydrogen or deuterium lamp for UV radiation. And there is the improvement for getting better signals or better absorptions. We have two radiations. That is, the radiation from grating is split into two waves. Okay, one reaches the reference and the other reaches the sample, and they transmit, this also transmits. Okay, this reference transmits the 100% of radiation because it doesn't absorb. Sample absorbs a part of it. Sample absorbs a part of it. Reference transmits the whole of the radiation that is falling on. And what happens here, the electrical component of the light energy comes into picture. And whenever that reaches a detector, that the semiconducting material that emits electrons, the electrons emitted by the light energy passing through reference different from light energy passing through the sample, because this is of less intense and this is more intense. This 100% transmitted, this is not 100%. A part is absorbed. So automatically there will be difference in the electrical component, and this difference will be detected and sent to the analyzer, and we get a spectrum. So this different spectrum is observed. So this is called a double beam spectrophotometer, which is very, very useful for getting a clear information about the absorption of the molecules. So organic compounds. First alkanes. How much time I have? Some 20 minutes more. We have started a bit late. Alkanes, all of them show sigma to sigma transitions.
Excuse me, sir.
Please.
Sir, please conclude as early as possible, sir.
Yeah. That I am asking you. See.
Okay, sir. Okay, sir. Thank you, sir.
And in the alkanes, the transitions will be from sigma to sigma star. Electrons in the sigma bonded electrons. They jump and go to antibonding orbitals, and the bond is broken. And these orbitals are less significant in the case of alkanes. And alcohols, ethers, amines, and sulfur compounds. So they have non-bonding orbitals, non-bonding electrons, and transitions that are possible are n to sigma star, and sigma to sigma star, and n to pi star. So n to sigma star also not important, and sigma to sigma star the same case, and they are often absorbed below 200 nanometers. Note how this transmission occurs, that is again from HOMO to LUMO. Highest occupied molecular orbital to lowest unoccupied molecular orbital, something like this. And here the electrons are transmitted from non-bonding. You see, from non-bonding to bonding. Even after this transition into the pi star orbital or sigma star orbital, the molecule is still stable because electrons are there. Electron density in the bonding orbital is more compared to electron density in the anti-bonding orbital. So therefore the molecule is stable. And in alkenes and alkynes, pi to pi star transitions are important. They are observed between 175 to 170 nanometers, and sigma star less significant. And these are the types of transitions that take place. That is from pi to pi star. This is pi bonding orbital and pi anti-bonding orbital. What is the difference between pi bonding and pi anti-bonding? That symmetry properties are different for this. So we have the positive and negative sign of wave function, and the anti-bonding orbitals are there reversed. So the bonding and anti-bonding orbital. And then organic molecules, the carbonyl compounds, n to pi star transitions are important. They occur around 285 nanometers, give good information about the molecules. And this is the pictorial representation of n to pi star transitions. And chromophores, substituent effects of, certain substituents change the wavelengths of the radiation, either low frequency side or high frequency side, or longer wavelength or shorter wavelength side. Then we can differentiate them. So this picture shows what are the effects of the substituents on the absorptions. Say if a molecule is having a pi bond and n to pi star transitions, they can be affected by the presence of some substituents. These substituents can change the absorption that is taking place here to shift to the low frequency side, that is 200 nanometer side, high frequency side or lower wavelength side. These are called hypsochromic shifts. And if any substituent changes the absorption towards the longer wavelength, that is bathochromic shift. And certain substituents can increase the intensity of the absorption. That is, the peak height may be increased or decreased. Now the substituents which increase the intensity of the absorption, they are called hyperchromic, and if they decrease the absorption, they are hypochromic. So like this, the substituents can affect the spectrum of the molecule. And what is the use of this? Yes, we have idea about the basic absorption of that functional group. Say for example, carbonyl n to pi star transition. And if a molecule with a carbonyl group and other substituent, it just slightly shifts, say for example from 275, if it shifts to 280, 290 like that, then we say there is a substituent and the effect of the substituent is something like that. So like that we can use this technique for knowing something about the substituents in the molecule also. So bathochromic, hypsochromic, as I have explained. And different groups, how they change the absorptions. Here I have given the table. Starting from, say, olefin, that is simple ethylene, 175. And here this is important, that is the epsilon value, molar extinction coefficient. This shows the signal intensity is more or less. And this is beta-diene. shift to 217, 2100 increases, and hexatriene, symmetrical in hexatriene, that is 258, further increase in the wavelength, 3500, and a beta carotene, that is present in the carrots, 465 nanometers orange color, 125,000, 1,25,000 epsilon value like that. And similarly, carbon compounds into pi star transitions 280, pi to pi star 181. And if you have another substituent, that is olefinic group, in conjugation with the C double bond O group, that changes. N to pi star is observed the same in 200, but pi to pi star transition changes to 230, that is longer wavelength, energy gap decreases. That we see in the next slide, some of the important aspects. Yes, what happens in the case of conjugated systems? In the conjugated systems, the energy gap between the LUMO and HUMO changes. Lowest unoccupied, say in unconjugated system, this is the energy, sorry. In unconjugated system, this is the energy difference more. When there is a conjugation, the energy difference between these two, between the available molecular orbitals decreases. So automatically the energy required is less with longer wavelength radiation. So like that, the spectroscopy can be used for knowing the structures. Now this is the summary of what we have discussed. That is, in the conjugation, say for example, ethylene, long gap, butadiene, gap decreases, in hexatriene further decreases, octatriene further decreases. Like that, this with increased conjugation, the energy required for the transition to take place is less, and that absorbs longer wavelength radiation, and intensity also safely. And we can also identify the isomers using this. Example here I have given is distance isomers of butadiene, and there is a gap. You see this picture. This is the trans diagram, molecular orbital energy level diagram, and the cis isomer energy level diagram. And here the gap between Psi2 and Psi3. Psi2 and Psi3 is more, and it absorbs at 270 nanometers. Here in the cis, the gap is less. It absorbs less energy radiation, 253, and this difference will help us in identifying the isomers. Cis trans isomers can be differentiated using the UV visible spectrophotometer. Something like that. This is the same about the compounds. And this is the arenes. And the conjugation. So like this, with increased conjugation, that is fused aromatic rings, will start giving compounds. Naphthalene is white in color, but phenolphthalein is highly colored. So like that, the UV visible spectroscopy helps in structural identification of organ. And last few slides, that is about the absorption of radiation by the inorganic compounds, especially transition metal compounds. Here you see the different volumetric flash, standard flash with the differently colored solutions. These solutions are the solutions of the salts of different transition metals. Now, how the transition metal compounds absorb radiation? We have seen the mechanism of absorption of radiation in organic compounds and how it will take place in the case of inorganic compounds. These are the different transition metal compounds of different colors: scandium oxide, vanadium, vandyl sulfate, manganese dichloride, different compounds in their color. What is the basis of the color in these molecules? Many transitions are in the visible region because they have D block elements, and the absorption is in the visible region. Transition metal compounds, they are colored, means absorbing radiation in the visible region. The selection rules for this are: the transitions obey the following selection rules. Important: delta S should be 0. That is the common for organic and inorganic molecules. There should not be any change in the spin state. If it is in the singlet state, in the transition also, after transition also, that should be singlet. If it is in the doublet state in the ground state, that should be doublet state in the excited state. There should not be any change in the delta, means change. So there should not be any change in the spin state. Such transitions are allowed. And all DD transitions are Laporte forbidden. That is, here you see why. Because only G to U or U to G transitions are allowed. G to U means gerate to ungerate or ungerate to gerate. Gerate and gerate are two symmetric properties or the symmetric property. Where there is center of symmetry, we call it as gerate. Where there is no center of symmetry, we call ungerate. So a transition should result from gerate, that is having center of symmetry, to not having center of symmetry, and or having a non-center of symmetry to center of symmetry. Now the simplest example for this to understand at a molecular level, not atomic level, orbital level, at molecular level. All octahedral molecules having similarly substituted ligands, then we call it is having center of symmetry. Octahedral molecule is having center of symmetry, whereas tetrahedral molecule is not having center of symmetry. So just that simple. So like that, the gerate to ungerate and ungerate to are allowed. All the DD transitions are forbidden because d orbitals are symmetric. Here symmetry we define based on the sign of wave function. If you notice the sign of wave function on opposite lobes, it is same, plus plus minus minus, plus plus minus minus. So like that, they are having center of symmetry, and such DD transitions are forbidden. Forbidden means they are not observed, and they are observed, but the intensity of such absorptions is very, very low. So like this, we will just explain the transitions in D1, D4, D6, D9 complex. So actually, in the transition metal complexes, we explain the transitions through the splitting of d orbitals. These are the ground state, the free metal ion transitions. These are the theoretically excited set transitions. And this is hypothetically explained by imagining that all the ligands are coming equal with equal distance in all directions. So energy of all orbitals increase simultaneously. But actually in the complexes, the ligands approach in a particular direction, and those orbitals aligned or oriented in that axis will experience more difference. Like that, in an octahedral environment, the 5 d orbitals split into two levels, T2G and EG. These are spectroscopic terms again, T2G and EG. So the orbitals split into a set of 3 orbitals T2G and set of 2 orbitals CG. These lower energy orbitals, higher energy orbitals. Now whatever electrons are there in the d metal ion, they will be distributed in these two sets of orbitals, depending on the energy gap between them. Depending on the energy, four electrons are there. In some cases, all the 4 electrons will be distributed here, 1, 2, 3, and 4. In some cases, electrons are distributed 1, 2, 3, and 1. So how this distribution takes place gives rise to the nature of the compound and electronic absorption. Now we see how this takes. These are the d orbitals and their orientations, and how the ligands approach. Ligands approach this direction, with that direction, x, y, something like that. And only those orbitals which are falling in the same direction experience more repulsion, and these orbitals experience less repulsion. Difference in energy arises. Say a chromium 2+ system with 4 electrons. Say in certain presence of certain ligands, the splitting in energy is less, that is delta is less, and 4 electrons distributed in all available orbitals of lower T2G and higher EG. But in case of certain other ligands, the energy gap is more, delta is more. So all 4 are electrons are. For accommodating this electron in this orbital, the system has to spend more energy. More energy means automatically it is less stable. So in this case, what are the examples? Here we have water is the ligand. Here cyanide is the ligand. When Cn minus is the ligand, it causes a greater split in the d orbitals, and water ligand causes less split. So electrons all are unpaired. Here 2 electrons are unpaired and 2 electrons are paired. The spin states are different for these two systems. Okay, and how do we make the difference between chromium aqua complex, hexaquachromium, hexacyanochromate? How do we make the difference? This is because the four unpaired electrons magnetic properties are different. Here only two unpaired electrons magnetic properties are different. And from the visible spectrum, this needs less energy, that is the longer wavelength radiation is observed, and here more energy is required, so shorter wavelength radiation is observed, high frequency radiation is observed. By the difference in the lambda max, we can differentiate a aqua complex from cyano complex. So like that, this technique is useful, something like that. The free ion, tetrahedral or trihedral complex is also differentiated, and the complex absorbs energy, electron change orbital, the complex changes energy state and absorption takes place, something like that in the titanium complex, and absorption is some bit like that. That is 510 nanometers is observed in the titanium complex. And what actually happens is in the ground state, the electron is here, and after absorption of energy 510 nanometers, the electron jumps from this orbital to this orbital. So this change takes place whenever light energy falls on the matter, and this gives information what type of energy is absorbed, what is the energy associated with the light, and what is the wavelength or the frequency, and from that we can say the molecule under investigation is so and so. And these are the D1, D6 transitions, and these are the spectrochemical series as we have seen in the case of earlier chromium complex, water and the cyanide. So in the case of water, the gap is less. In the case of cyanide, gap is more. So we can arrange the different ligands in the increasing order of the splitting capacity, that is called spectrochemical series, and weak field water and strong field cyanide ion and carbon monoxide, like that. So like that, this is the spectrochemical series. When the ligand changes, the absorption of light by the transition metal complexes also change. And
Excuse me, sir.
so I am stopping it now. This is not that important.
Okay.
Okay. So, thank you. Thank you very much, Mr. Ramohan and Upender, for nice introduction.
Thank you, sir. Thank you so much. Thank you, sir.
Thank you, sir.
Okay, thank you very much. Thank you.
Thank you, sir.
Thank you, sir.
See you all. All the best.
Okay, thank you, sir.
Now, interaction session with students and participants. Any questions from?
You can tell, you can give my mail ID to them. If they have any questions, they can post. I will send the answers immediately. I don't have
Okay, sir.
Is Vital ready?
Please send an email, sir.
Okay.
Okay, sure. I will send one day national webinar WhatsApp.
Thank you.
Any questions?
Good morning, sir.
Hello, sir.
Morning.
Thank you, sir, for giving this wonderful lecture for us.
If it is useful, I am very happy.
Yes, sir. It's very useful for us. Sir, can you please post it a PPT on us groups?
Yeah, I'll try. I'll send it to Rama.
Yeah. Thank you, sir.
Okay.
Hello, sir. Good morning, sir.
Good morning.
Sir, I have one question.
Please.
Regarding selection rules. In selection rules, molar absorptivity coefficient is also there, no? They will say if it is less than 10.
That is also, if a transition is allowed, the coefficient of expansion is very, very high, and you get a very intense colored band. If it is in the visible region, the intensity of that is very high. If the absorption is forbidden, not allowed, then the intensity of that absorption is very, very weak. And the values, epsilon values will be in order of few tens. But in the case of the allowed transitions, it will be in the order of few thousands.
Okay, because in some books they have written that it should be greater than 1,000, and in some books it is written that it should.
It is generally for allowed transitions more than 1,000. I told you in the order of thousands. The values are in the order of thousands.
Amma.
Okay.
Thank you, sir. Thank you very much for excellent presenting as lecture on UV spectroscopy, how molecule absorb energy from ground state to excited state and observe electronic transition and can be determine quantitative of the molecules. Sir, you said good difference between natural spectrometer and man-made spectrometer. Sir, you lecture very informative knowledge to the students as well as participants. Sir, once again, heartfelt thank you so much on behalf of MSc 5-year Integrated Chemistry, Palamuru University, for your spending valuable time in this webinar. Thank you very much, sir.
Thank you. Thank you very much. I am very pleased to share my knowledge with the students.
Sir,
Nice.
please send me your email, sir.
Okay, next. I will send. I will send this.
Okay, thank you.
Sir, please continue.
Okay, thank you.
So now, next session, introduction of the speaker, Professor Vital sir by Mr. S. Ravi Kumar, Faculty, Department of Integrated Chemistry.
Thank you, sir. Sound is Thank you, sir. Good morning to all. I, S. Ravi Kumar, Department of Integrated Chemistry, deem it a great honor and privilege to invite today's speaker, Professor M. Vital, sir. Sir completed his PhD in 1986 from University of Hyderabad. Sir has 49 years of research experience ever since joining in MPhil in 1979. He guided 18 students, obtained PhD under his supervision. Presently, 6 PhD students and 2 PDF students are working under his esteemed supervision. He has total teaching experience 32 years. Currently, he is BSR faculty fellow. He served as administrative officer in various fields such as Board of Studies, set coordinator, additional controller of examinations, chief warden, etc. His areas of research interest: solid state chemistry, material science, nanomaterials, preparation of nano titanium dioxide suitable for dye-sensitized solar cells, preparation and characterization, ESR, mass bar, conductivity, magnetic properties of borates, dilafluorates, orthopherates, favoscosite, nasicones, and other solid metals. He published a research publication in reputed journals is about 152 papers. He has membership in the reputed academic bodies. He is a member of AP and Telangana Academy of Sciences. He is a member of Materials Research Society of India. He served as brainful scientist. He is selected as brainful scientist at Korea Research Institute of Chemical Technology, South Korea. He worked as a reviewer about 25 international and national journals. Thank you very much, sir. I am requesting you, sir, to deliver a lecture on IR spectra to enlighten all participants and students, including all eminent faculty also. Thank you very much, sir. Please continue your sessions.
అది పవర్ పాయింట్ ఓపెన్ చేయాలి కదా.
Yes, yes, sir. PowerPoint.
Yes, sir.
Yes, sir. Okay, sir.
Yeah.
Okay.
Yeah, sir.
Yes, sir. Screen share started, sir. Please continue, sir.
Please continue, sir.
Waiting is
Yes, sir. Okay, sir.
Can you see the slide?
Yes, sir. Yes, sir. It's visible now, sir.
It is visible.
It is visible. Is it audible?
Yes, sir. Audible.
We are listening your voice, sir.
Wonderful. Wonderful. I should say that good morning still, because we are at 11:38.
Yes, yes.
Very good morning to all the students. And I would like to express my sincere thanks to Palamuru University, MSc 5-year integrated faculty members, and Mr. Professor Murthy, who has actually initiated this discussion. Or this was possible because of the efforts taken by Professor Murthy. But unfortunately, see, 1 hour lecture, and that too actually a webinar lecture, possibly may not be sufficient for MSc students to understand the spectroscopy. I mean, infrared spectroscopy. Actually, first year students, it will be having 1 unit, 1/4 of a paper, and it requires about 12 to 15 hours, 60-minute hour lectures. So it is meaningless actually, to compile what we are supposed to teach in about 12 to 15 lectures in about 1 hour lecture. But in the present scenario, at least, we should have a flavor of what is, molecular spectroscopy. So I thought that, I should introduce you a few concepts of infrared spectroscopy. But before we go into the actual discussion, I would like to make a statement that, PowerPoint presentation lectures possibly will be useful only when you want to present a large quantum of data in the shortest period of time. But for fundamentals, understanding the fundamentals, possibly the chalk and talk is the best. Next slide. Okay. Yeah. Now, before we actually go into the, the fundamentals of infrared spectroscopy, we need to understand a few terms which are very useful, or which will lay the foundation to understand the concepts. I have listed here, but unfortunately I am not defining, but I will be able to tell you, the meaning of each and every term. Possibly I suggest that if you are an MSc student, I suggest you please note down this textbook, Fundamentals of Molecular Spectroscopy. Fundamentals of Molecular Spectroscopy by Colin Barnwell and Elaine McCash. Now, the cost of this book is around 200 rupees, plus minus 20 rupees. And possibly in these days, each student can afford to pay about 200 rupees per semester for all exclusively for books. Now let us go into the actual terms. Possibly, I may skip a few, because if you can buy this textbook, that is going to be an asset for you. And I wish that if there are 30 students in the class, all the 30 should buy this textbook, so that you will be able to read it whenever you are free. Now, coming back to the terms, The light, actually, without light, we will not be able to survive. It is the source which is required for measurement of all branches of spectroscopy. Then what is the frequency? The number of cycles per second is actually the frequency. What is wavelength? Wavelength is actually the successive distance between two successive crests or troughs. Then wave number. Wave number is the inverse of wavelength is actually wave number. Then velocity. Velocity is the distance traveled per unit time. Now, recently I asked a simple question to my MSc students that as Professor Jagannatha Swami has given you the various branches of electromagnetic radiation like X-rays, gamma rays, UV rays, IR rays, and then microwaves, etc., gamma rays, etc. What is common for all these branches of electromagnetic radiation? The velocity is common because all photons will travel with the same velocity. That is why the velocity is a universal constant. It is given by 3 to 10 power 8 meters per second. Then we need to understand absorption spectra and emission spectra. Possibly, there is a small difference between these two, in the sense that in the olden days, the absorption spectra is seen by a black background with white lights, and the emission spectra is seen as a white background with black lines. But these days, absorption and emission spectra looks similar unless in the latter, that is in the emission spectra, the excitation frequency is mentioned. Then there are 3 important, 8, 9, and 10. One is called a resolution, slit width, and intensity. Now, resolution is the ability of the spectrometer to closely spaced lines. Now, this is called resolution. Now, slit width. Now, slit width is actually a parameter which governs the resolution of a spectrometer. In other words, if I want a high resolution spectrum, what should be the slit width? If I want a low resolution slit width, low resolution spectrum, what should be the slit width? Now, slit width plays an important role in resolving the molecular spectrum. Then finally, the intensity. Very often actually I ask the students, what do you mean by intensity? But no student will be able to answer it properly for the simple reason that in majority of the textbooks, this will not be mentioned. Therefore, we need to understand that. So intensity refers to the number of photons falling per unit area. So that is what is called the intensity. Then a few terms, a few equations are also useful, required for us. For example, the optical density or absorbance is actually log I naught by IT times, that is equal to epsilon, Morar extinction coefficient, times concentration, times the path length. Now, in the normal spectrophotometer or colorimeter, we measure the optical density, which is actually a unitless quantity. And in infrared spectroscopy, we need to measure the transmittance also. If we have all branches of spectroscopy like UV spectrum, UV spectroscopy, IR spectroscopy, NMR, ESR, mass bar, XPS, photoelectron spectroscopy, and then whatnot. There are a large number of spectroscopic branches. But a mass spectroscopy, actually, I will not consider as a branch of spectroscopy for the simple reason that mass spectroscopy will not be involved with Hamiltonian. That is actually a separation technique. But this term, transmittance, is used in only 2 branches of spectroscopy. One is actually infrared, the other one is mass bar spectroscopy. In all other branches, the spectrum is measured in the absorption absorption mode or absorbance mode. Nowadays, infrared spectra also is measured in the absorbance or in the absorbance mode as well. Now, having said that, answer having said that, the different regions of the electromagnetic spectrum I am giving in this form of in the form of a table. But please do remember that one need not by heart this. But if you can remember, for example, you just follow the wavelength. ఒక్క నిమిషం ఏమైంది పెట్టేసాక మన ప్రాబ్లము వాళ్ళ ప్రాబ్లం ఇది కనబడుతుందా వాళ్ళకు స్క్రీన్ కనబడుతుంది అప్పుడు పిల్లలకు ఇదే కనబడుతుంది ఇట్లా కనబడుతుంది కానీ సిస్టమ్ ఈజ్ ఆల్వేస్ ఎ సిస్టమ్. లైట్ ఇటు ఉండాలనా అటు ఉండాలనా? అక్కడి నుంచి లైట్ వచ్చేది పడదు.
शेयर कंटेंट
దానిలోకి వెళ్ళాలి కదా మనం. షేర్ కంటెంట్ స్క్రీన్ స్టార్ట్ బ్రాడ్కాస్ట్ అది ఇప్పుడు ఓపెన్ ఉంటుందా? ఇది కదా. ఓకే, can you listen now? Hello?
Okay, sir.
Can you listen?
Yes, sir. Listening, sir.
Yeah. So I was telling about the few important terms which are going to be very useful for any branch of spectroscopy. I have listed this, and I advise all the students to buy this textbook. And if I happen to see you personally, my first question will be that how many of you have purchased this textbook, because this is very essential. Of late, I have seen that the students are not purchasing textbooks. Without textbooks, possibly, we will not be able to understand the fundamentals properly. Now, let us go to the actual equation. The equation is that optical density is given by epsilon, molar extinction coefficient, times concentration, times path length. And I told you that in the infrared spectroscopy, we use that in the transmittance mode, and the transmittance is given by IT by I0, which is equal to e to the power minus ACL. This is actually, it is seeing as E minus ACL. It is e to the power minus ACL, or minus absorption coefficient times concentration times path length. Now, the various regions of electromagnetic radiation, as explained by the earlier speaker, is actually listed in a different form, in the sense that which radiation brings what change in the
molecule. For instance, if you take gamma rays have sufficient energy to excite the nucleus. Not, other than gamma rays, no radiation can excite the nucleus. Similarly, X-rays, if you see that X-rays are having sufficient energy to knock out an electron from the core level. Core here refers to 1s, 2s, 2p, etc. Now, what do you actually gain from XPS or X-ray spectroscopy? You actually get what is called binding energies. We always say that the hydrogen, the electronic configuration is 1s1, and what is the amount of energy required to release the electron? We call it as a first ionization potential, which is 13.6 electron volts. But how did we get this? This we got it from XPS only. Similarly, ultraviolet radiation, possibly it will bring a change in the valency shell electron distribution. Infrared spectroscopy, which I am going to touch upon, will bring about certain changes in the molecular configuration. Here, molecular configuration refers to that it is not going from one R to S or S to R. It is not that way, but it is going to slightly change the relative positions of the atoms present in the molecule. Now, when it comes to the infrared spectroscopy, see, I have given a very lot of introduction, which I cannot read, but it will be available with your head of the department, Mr. Ramohan. But what is important is that you should remember the regions in at least in one of the scales. For example, IR region is about from 500 to 4,000 centimeter minus 1. Whereas far IR is below 500 and near IR is above 4,000 centimeter minus 1. I also would like to tell you that you must become familiar with all conversion units. Unfortunately, I do not have time actually to make you familiar with the energy conversion unit. Possibly if I get an opportunity to in a class where I can see 30 students, then possibly I will be able to make you understand that this is how one has to convert the energy units. Because energy units conversion, if you know, you can actually do a lot of things in spectroscopy. Particularly, you can solve many problems. So my point is that all the students must become familiar with energy conversions. For example, if I ask you that how to convert energy in joules to energy in centimeter minus 1. Unfortunately, in this webinar lecture, I cannot show you, but simply I can tell you that energy in joules can be converted to energy in centimeter minus 1 by just dividing energy in joules divided by Hc. If you divide by Hc, the energy in joules divided by Hc, you will get energy in centimeter minus 1. Now, why do we require this? We require because in majority of the spectroscopic branches, we measure the energy in reciprocal centimeters, and therefore we need to remember this. Then I have just given one slide about the principle of IR. Don't worry about this, but how actually we should try to understand the principle involved in the infrared spectroscopy. We should begin with what is called a simple harmonic oscillator, or we say consider a very simple molecule such as HCl, which is a diatomic molecule. Now, if you take a diatomic molecule, no, Rammohan, I am listening some sounds. Is it some disturbance is coming? Rammohan.
Sir.
I am listening some sounds.
Yes, yes, sir. I sir. Hello. Hello, sir. Sir, మీరు unmute చేసుకోండి సార్. Sir, please. Hello, sir. Hello, sir. Sir. Hello. Sir.
Mute చేశాను. Are you able to listen now?
Yes. It is now okay, sir. Please.
Now, okay, I'll continue.
Sorry, sir. Okay, sir. Continue, sir.
It's okay. Yeah. See, principle of infrared spectroscopy can be better understood by considering a diatomic molecule such as HCl. Now, HCl at room temperature is a gas, but assume that you are cooling it sufficiently so that it will become liquid and sufficiently so that it will become solid. Now, in gaseous state, the HCl molecules have the freedom to move anywhere. Now, if you take HCl liquid, possibly the H and Cl may not move, but within that volume, it can still move. In the solid, HCl solid, there will not be a possibility of movement at all. But quantum mechanics says that even in the solid state, the atoms are moving within their equilibrium positions. In other words, the atoms in the molecules are in constant motion, irrespective of its phase. Therefore, we should try to understand by taking a simple harmonic oscillator equivalent to a diatomic molecule. Now, if you do that, then quantum mechanics readily gives the solution for simple harmonic oscillator, and then we can add that or borrow that from simple harmonic oscillator and apply to a real molecule. Now, diatomic molecule is considered as a simple harmonic oscillator, and we borrowed the equations. Now, those equations I am going to give you, as I'm going to skip this because these are not essential. Now, in this diagram, I have shown that H and Cl, chlorine, and then, can you see this? Yeah, the H as well as Cl. Now, Cl I am fixing because it is heavier atom, and then moving hydrogen towards chlorine and away from chlorine. Now, this is a simple motion, which we call it as actually a stretching motion. Now, this is equivalent to a simple harmonic oscillator. And then if you apply the quantum mechanics to it, you get the frequency at which hydrogen is moving towards chlorine and away from chlorine, given by an equation which is given here. Omega bar OS equal to 1/2 pi c under root k by c. All the students, please remember that you must by heart this. By heart this equation. This is relevant for you. Now, it says that the oscillation frequency is proportional to a force constant k under root and inversely proportional to the reduced mass. In other words, the force constant is nothing but the ability of the two atoms to bind itself. In other words, if force constant is more, then it becomes more strong because it is difficult to break the bond. For example, you take C triple bond C, C double bond C, C single bond C. For C triple bond C, the force constant will be higher in value compared to C double bond C, which in turn is higher than the force constant of C single bond C. So this equation one has to remember, and the another equation which is relevant in the present context is this equation, where there is a small mistake in this equation. Mistake is that it is EV equal to is missing. Now, please remember this. EV equal to, open the bracket, V plus half H omega bar OSC joules. I repeat once again, there is a mistake in this equation. EV equal to V plus half omega bar OSC joules, where V is called vibrational quantum number and it takes values 0, 1, 2, 3, 4, 5. Now, if it is a classical classroom, I would have asked a simple question. Even now also, I will ask the question. Why we should take the values 0, 1, 2, 3, 4, 5? Why not V equal to 1.1? Why not V equal to -1? Possibly I will be able to answer this because I should give you some questions also for you to think. Now I can give the answer immediately, but that will prevent you in going through the certain textbooks. Therefore, I will not give the answer, but anybody is interested, my phone number and my mail ID will be with Ram Mohan, and you can contact me at any time after 8 p.m. every day. Now in the next line, I have shown that the energy in centimeter minus 1, I can convert, as I said earlier, energy in joules divided by Hc gives rise to the energy in centimeter minus 1. Now this equation and the earlier force constant equation are the two very important for infrared spectroscopy. Now if you see this equation, V goes from 0, 1, 2, 3, 4, 5 or any positive integer. Suppose the lowest V value, that is V equal to 0, if you substitute, EV becomes 1 by 2 omega bar OSC, which we call it as a 0 point energy. This refers to that the energy of a solid or any molecule, even at 0 K, is not 0. But it is a finite value. This is where actually classical wave mechanics failed and quantum wave mechanics actually emerged. Because classical wave mechanics says that at 0 K, the energy of the system is 0. But quantum mechanics says that energy is not 0, even at 0 K. Now this equation is in accordance with the quantum mechanical formulations. The existence of 0 point energy is in accordance with quantum mechanics. I have recently seen a few years back in one of the national examinations that cite one example for the validity of quantum mechanics over classical wave mechanics. You can state that the existence of 0 point energy itself is a proof that quantum mechanics is prevailing. Now let us not go to the, other than that, because, I can talk about quantum mechanics for quite a bit of time without actually going into the infrared spectroscopy. Let us not go into that. Now, let us go to the next one, selection rules. Now, as a Professor Jagannatha Swami also actually nicely explained about the selection rules. Now, whatever transitions that we are seeing in the spectroscopy are in accordance with the selection rules only. Without selection rules, actually, we will not be able to invoke any transition. So any transition that is observable is in accordance with selection rules only. For harmonic oscillator, the selection rules are delta V equal to plus or minus 1 only. Please remember this. Now, when I say this, then you have EV equal to 1, EV equal to 2, EV equal to 3. As V can be changed, the E also changes. So you can plot actually. Now, this diagram is given in the Barnwell only, from Barnwell only I have taken. Now, this is what actually you should actually generate, because once you know the omega bar OSC, you can actually calculate the energies. So whether all transitions are possible or not. Now, the theory says that it is not possible. Why it is not possible? In principle, it may be possible, but in reality, it is not possible, because you need to have the molecules in the V equal to 0, V equal to 1, V equal to 2, V equal to 3 to observe the transition. For example, V equal to 0 to V equal to 1, or V equal to 1 to V equal to 2, or V equal to 2 to V equal to 3. If you take the difference, all the transitions will give omega bar OSC only. So once you get only one transition, whether this one transition is from V equal to 0 to V equal to 1, or V equal to 1 to V equal to 2, or V equal to 2 to V equal to 3, or any other, it is difficult. But once again, quantum mechanics comes to our rescue, because the Boltzmann distribution says that V equal to 0 and V equal to 1 population difference, if I take it, if V equal to 0 is 100%, then V equal to 1 will be only 1%, less than 1%. In other words, V equal to 1 is populated compared to V equal to 0 by less than 1%. So less than 1% is actually meaningless, or we say that it is close to 0. In other words, if at all there is any transition, it must occur only from V equal to 0 only. So this transition V equal to 0 to V equal to 1 is called fundamental mode of vibration. So this is essential for all MSc students to remember that if anybody is asking what is the fundamental mode of vibration, immediately you should state that the transition which occurs from V equal to 0 to V equal to 1 is called fundamental mode of vibration. Normally, all the fundamental modes of vibrations are very strong because their epsilon value will be very high. Now, what happens if you heat the molecule actually? Because you look at this equation, practically I wanted to explain, practically I would like to show you, but unfortunately I cannot show you in the webinar class. Now you take V equal to 1 divided by V equal to 1. I have given the Boltzmann distribution equation in this. Now if you take 300K and you take 400K, then you will see that V equal to 1 gets population. In other words, as the temperature increases, the transitions from V equal to 1 to V equal to 2, V equal to 2 to V equal to 3 becomes probable. And such bands are called hot bands. Hot bands are the vibrational transitions which occur from V equal to 1 to V equal to 2, V equal to 2 to V equal to 3, and so on. Now there is no counterpart, that is, there is no cold band. We only have hot bands. Okay. Now let us go to some other terminology which is very often used in infrared spectroscopy, and that is overtones and combination bands. But before to understand the overtones and combination or difference bands, we need to know what is called enharmonic oscillator. Now, harmonic oscillator is an ideal situation where the oscillations are harmonic in nature. That is, stretching or compression goes equally. Now, unfortunately, the real molecules are not harmonic oscillators. It is similar to that of your ideal gas equation and real gas equation. How many gases do follow ideal gas equation? There are very less in number, and that too certain conditions, like very low pressure, very high temperature, something like that. Similarly, in reality, the molecules are not harmonic, they are enharmonic. So if they are enharmonic, then that enharmonicity must be introduced into the equation. Now, for us, one need not worry because enharmonicity is already introduced, and then equation is modified as this equation. Now, this also one should remember. Please, higher order terms we are neglecting, but the first two terms are sufficient. Now, EV equal to V plus half omega bar E plus V plus half whole squared omega bar E XE, where this XE is called enharmonicity constant, and it is unitless. Please remember that it has no units, and its magnitude is between 0.01 to 0.05. Now for enharmonicity, the selection rules are delta V equal to plus minus 1, plus minus 2, plus minus 3, etc. Now if it is a V equal to, that means plus minus 1, plus minus 2, plus minus 3 means in the next diagram, I have shown that V equal to 0 to 1, V equal to 0 to 2, V equal to 0 to 3. Now if you notice the first one, V equal to 0 to V equal to 1, delta E equal to omega bar E. See, bar is missing once again. There are certain things which I need to tell you continuously. Bar, if you put, it is a wave number. If you do not put, it becomes a frequency. Now, delta E equal to omega bar times 1 minus 2 XE. Now, in the harmonic oscillator, XE was 0. Therefore, it becomes omega bar E only. But in the enharmonicity, this 1 minus 2 XE term is introduced. Okay. Now, The second transition, V equal to 0 to V equal to 2, delta V equal to plus 2, and delta E equal to this becomes now. So for a MSc student, you should not do like this. You should take the equation, the above equation, and substitute V equal to 2 and V equal to 0, and then do the calculation. If you do the calculation, it becomes 2 omega bar E times 1 minus 3xe. I once again impress upon the MSc students, please do not copy these equations in total. You must do it on your own. Otherwise, there is no meaning. See, it's like this. If I say that so-and-so sweet is so good, it is so tasty, you should not believe unless you taste it. Similarly, I have given these equations. There are mistakes in this because, sometimes I miss, I have to frame it. So during that, I have missed omega, putting a bar on omega. So you should not believe this equation, but you believe the equation which is given in the Barnwell, and convince yourself that you get for V equal to 0 to V equal to 2, it is delta E equal to 2 omega bar E 1 minus 3xe. Then you will realize that, oh, this equation, I got it verified. Similarly, the next one, V equal to 0 to V equal to 3, is delta equal to 3 omega bar times 1 minus 4xe centimeter minus 1. Now, one important parameter which you should notice is that fundamental mode, for second one is the first overtone and the third one is second overtone. If you neglect the parameter enharmonicity constant, they are in the 1:2:3 ratio. In other words, fundamental mode, if you observe at 1000 centimeter minus 1, then first overtone will be around 2000 centimeter minus 1. Then second overtone will be around 3000 centimeter minus 1. But you can observe only first overtone, but second overtone will be having very less intensity. Normally, you will not be able to observe at all. So you observe only fundamental mode and a first overtone. Now, Barnwell has very nicely described. For such of those students who would like to understand and then try to compete with the rest of the students, you should try to solve the
Sir, hello. Sir, your voice is not audible, sir. So, please recheck, sir. Hello. Sir, your voice is not audible, sir. Please recheck it, sir.
Sir, your voice is not audible, sir.
Sir, your voice is not audible, sir. Is it clear, sir? Please recheck it, sir. Once again. Hello. Sir, your voice is not audible, sir. Hello. Sir. Hello. Sir. Sir, is it network problem, sir? Please recheck it once again, sir. Hello. Hello, sir. Problem will be rectified. Not due to network problem. Then my number of sir. Hello, sir. Hello, sir. Sir, moderate. Hello. Hello.
సార్ను రీజాయిన్ కమ్మని చెప్పండి.
Sir. Hello, sir. Sir, okay, sir.
Join ayana?
Okay, sir. Okay, sir. Okay, sir.
Right.
Now
Right.
it is audible, sir.
Right.
Okay.
Okay. Yeah. Now.
Sir, carry on, sir, please, sir.
Yes, I'm doing that. And the rotational vibrational spectrum of simple carbon monoxide is shown in the next diagram.
Sir, screen రావట్లేదు, sir, please.
Screen రావట్లేదా?
Okay, sir.
వచ్చిందా?
No, sir. No, it is visible and we audible, sir. Okay, sir.
Okay, right. Now, kindly see this diagram. That is the carbon monoxide infrared spectrum. Now, if you look at this in the high resolution, you will see that there are many lines in figure A. There are many lines. Actually, the band center is around 2150. All the students, please notice this. 2150 is the band center, and on either side of this, there are equidistant lines. Now, that is the rotational fine structure. Now, on the right side, you will see that a small intense peaks around 40 to 50 band center. Now that is actually the first overtone. First overtone of carbon monoxide. Now, if you take 2140 as the fundamental, 2150 as the fundamental mode of vibration, then double that will be around 42 to 4300, and exactly around that place, your first overtone is appearing. So this is what is required. You see the intensity of fundamental mode and you see the intensity of overtone. Now, unless you see the textbook, you will not be able to understand. Therefore, my simple submission to all the MSc students, I am going to monitor that how many of you have purchased the textbook, because without textbook, these days I am upset due to the lack of purchase of these books by the students. It is unfortunate, you know. Nowadays, books are available in the library, books are available everywhere, and you can own it actually. So let us not worry too much about that. Now, this is actually, you know, some of the equations which I solved personally for you only, that delta V equal to the equation I have given, and then I solved it. Practically, I have done it, and then see that, you know, you are getting omega bar 1 minus 2xe, fundamental mode, first overtone, second overtone, and then hot band. Now, the story will not end with diatomic molecules. You will be having polyatomic molecules. Now, once polyatomic molecules are there, the theory becomes complicated. However, for this also, there is a solution. Solution is that we require only those exchanges or those displacements which will bring about a change in the dipole moment. And if you look at that, for vibrational degrees of freedom, for linear molecules, it is 3n minus 5, and for non-linear molecules, it is 3n minus 6. For example, if you take benzene C6H6, so there are 12 atoms. So 3 into 12, 36, and minus 6. So 30 vibrations are expected. You may not observe all, because some may be having low intensity, some may be degenerate, and therefore you will observe only less than 30. Now, since the time is very less, I will now concentrate only on one aspect, that how to record the infrared spectrum of a sample. Can we say that, can we record the infrared spectrum in gas, liquid, and solid phase? The answer is yes, you can record that. And for gas samples, you require a gas chamber, a quartz gas chamber. It is very difficult to record the gas spectrum, infrared gas spectrum, infrared spectrum of the gas. But you can record the UV visible spectrum of gas very easily, but not the IR spectrum of a gas. Now, if it is a liquid, then how to record the infrared spectrum? Now, if it is a liquid, you should have a liquid probe in the infrared spectrometer. Normally, we take sodium chloride crystals, which is of 3 centimeter by 2 centimeter by 1 centimeter width, and then put a drop of liquid sample between the two sodium chloride crystals, and then a thin film of the sample will be prepared, which is sandwiched between 2 sodium chloride crystals, and these 2 sodium chloride crystals put together will be put into the infrared spectrometer to record. Now, a simple question should come to your mind: why sodium chloride crystals are used? The answer is that sodium chloride is infrared transmittive, in the sense that it does not absorb the infrared radiation, and therefore it is used. Then what about solids? Solids, we actually take a small amount, about less than 5 milligrams of the sample, and mix with 20 to 30 milligrams of the KBr, and then prepare a thin pellet, and then put it in the infrared spectrometer. Then you can record it. Now, there are many things actually I planned, but since that it is going to be disconnected, possibly I have to stop it. The PowerPoint presentation will be with Ram Mohan, but I suggest all the MSc students, do not use PowerPoint for your MSc classes. Use only textbooks. Please solve all the equations. then only you will be able to understand the principles correctly. Now I have to stop this because it is going to be disconnected in another 2-3 minutes. That's what I was told. So if 1 or 2 questions are possible, I still actually will try to answer. And if I do not answer, I will give you the source from where you can get it. Or alternatively, any student can contact me because Rammohan is having my mail ID and phone number. Okay. Thank you for giving me an opportunity again.
Any questions from participants, sir? Hello? Hello?
Students, particularly students.
Yeah, yes, sir. Yes.
Rammohan. Rammohan. See, this PowerPoint presentation, everything is all right. But if there is an opportunity to teach the MSc integrated 5-year students,
yes,
I think I will be pleased to give a lecture, because that is, eye to eye is much better than this webinar class. Normally, I do not like. I just said yes because it's an opportunity to teach in the online also.
Yes,
okay?
yes.
So, but I will be more pleased to have a direct interaction with the students. Okay.
Okay, sir.
So
Thank you, sir.
ask the students.
Sir, any questions from participants, especially students, sir, please? Please, we have less time. Okay, please raise your hand. We have doubts.
Next session after.
Next session after session also will be continued. We will give feedback forms after session, after completion of our program. And at 1:30 we will give and we will start another session. So please available. All are requested. Okay. Thank you. Speakers also will join with us, sir. Thank you, sir. And very much, sir. You explained very well in IR spectra. It is IR spectra is absorption spectra. The vibrations you explained, vibration modes, stretching vibrations and bending vibrations. And according to selection rules, there is without selection rules, there is no transmission possibility. So, and according to harmonic oscillator, the bonding can be stretched to an extent. And we know your time ICS. Some of you we look forward to your participation in future events. Thank you very much, sir.
Next session.
Next session will be started at 1:30 p.m.
Okay.
Okay.
Continue.
Hello?
Can I discontinue? Can I
Yes,
close
sir.
the
Sure, sir. Sure, sir. Thank you, sir. Thank you. All participants are requested and all speakers also requested. You rejoin at 1:30 p.m. without fail. After completion of webinar, we will give feedback forms and e-certificate will be issued to you. Thank you very much. Thank you.